You the first industrial talk of this week. So I'm from Framatome, a DOC research center, which is located in Eugene, not so far from here. I will talk about what I call the optimized manufacture of nuclear fuel cladding tubes, and with the help of numerical modeling of processes and microstructure evolution analysis. So you will see that I will speak a little about recrystallization, but I wanted to give you the whole picture of manufacturing route optimization, including microstructure optimization. So first I will introduce what we do in Framatome, some word about nuclear fuel and zirconium alloys, give you some example of zirconium components manufacturing and modeling, and we will see step by step how we try to improve the processes to get the right quality at the end. So starting from upstream processes up to the billet microstructure for extrusion process, and then the cold rolling process to the final product. So first, Framatome is working in the nuclear industry. We are designer and supplier of nuclear steam supply systems. So it includes large projects, manufacturing of big components in Le Creusot and Chalon-sur-Saône, and also the manufacturing of the fuel, nuclear fuel, which is at the end, at the center of the nuclear core. So I belong to the zirconium fuel business unit, and our goal is to develop, design, and license, and fabrication, of course, fuel assemblies for all type of nuclear reactors. So this is here an example on the right of pressurized water reactor fuel assembly. Okay. So to make this kind of assembly, we have to produce different zirconium alloys components. First, the main one is the cladding tubes. So it's zirconium tubes, and we put inside the UO2 pellets. We have also some guide tubes. So we have the cladding tubes. There is also some guide tubes for the control bars, but also for some instrumentation of this assembly. We have to manufacture also some flat products, strips, in order to manufacture these grids. And at the end, we have also bars, just to make some plugs, in order to have plugs at the end of the tubes. So why these strange zirconium alloys? We use it in nuclear industry thanks to the low neutron cross section, because it's needed to have a good reactor efficiency, because the neutrons have to go from one uranium atom to another in order to have the fission reaction. And zirconium alloys have also a good resistance for corrosion, creep, and irradiation during all the life of the fuel. So to manufacture these products, we have several processes, and for each of these processes we use currently numerical modeling in order to improve the process parameters. So it starts from the extractive metallurgy, because we produce our own zirconium metal from zirconium oxide. Then we have to manufacture ingots thanks to VR process, forming processes with forging, extrusion, rolling. So we run computations for this with the Forge NXT software. And we have also models for induction heating, heat treatments, and quenching, and also for some inspections of the final products. So I come to the center of my presentation. I will give you an example for this kind of defect that we can have sometimes in manufacturing. This can happen during the cold rolling process, and we know by experience that three main parameters can affect this type of defects. First one is microstructural heterogeneities, so namely a bad rock crystallization can be the cause for this. It can happen also if there is already surface defects on the product during hot extrusion. So it can be folds like this or scratches. And finally, if the rolling process is too severe compared to the ductility of the alloy, for sure we will have this kind of defects. So I will explain you how we can optimize this kind of defect. First, I will start from the upstream processes. So this is the process used to manufacture the zirconium sponge with the nuclear quality. So the first process, which is very important, is to separate hafnium from zirconium, because at the natural state, hafnium always comes with zirconium. And we use as a separation process a distillation column, in fact, which is near to Grenoble. So you can, okay. Then we have, and for this, we use chloride. So we have at these steps zirconium and hafnium in the form of tetrachlorides. Then to have the zirconium, metallic zirconium, we use the Kroll process. So it's the same process used for titanium sponge. And here we have a reaction with tetrachloride, zirconium tetrachloride and liquid magnesium and gaseous tetrachloride, and this gives us magnesium chloride plus zirconium, metallic zirconium. And at the end we have a mix of this plus some residual zirconium tetrachloride, and with the vacuum distillation process we are able to remove residual magnesium, magnesium chloride and zirconium tetrachloride. And at the end we have this kind of cake, which is porous, and then we crush it, and we have these little rocks of what we call zirconium sponge, because it's porous. And what is important here is that these processes gives the chemistry of the sponge, including some residual elements that can be very important for the microstructure. Then we have the VR melting process for ingot manufacturing. So it's a consumable electrode in a furnace under vacuum. We have a very high current going through the electrode. An electric arc is forming here, and the metal drops by, we have droplets of liquid metal going into the crucible. And then we have a copper crucible with highly cooled with water, and so the ingots solidify while we continue to melt the electrode. And this process is also important for microstructure at the end, because it will give us the final content of the final chemistry of the ingot, including some impurities. And I have here the example with numerical modeling of the chlorine content in ppm, so it's very low content in our ingot. And you will see later that this few chlorine content can have a very large impact on the microstructure during the rest of the manufacturing process. Okay. Then we have the forging step. I have a video, maybe it's working, just to illustrate. So it's a classical forging process, a cogging process, with open, very simple tools, in fact, at this temperature. So we have multiple heating, forging, cutting, heating steps, and so on, in order to reduce the diameter of the ingot at the end. So if you want, you can see this in Eugene. It's not so far from here. And so at the end, we have this kind of forged bars that we will cut into billets for hot extrusion. And we manufacture also flat products for hot rolling and cold rolling. This step is important because we have very large deformation, but at the end, the microstructure during this step is not so important because we will have then a quenching process. So we will erase the initial microstructure. So for our alloys, what we call quenching is we heat in the beta phase up to 1000 and something degrees. Then we have a controlled cooling with a given cooling rate. We have gemination of alpha plates within the X-beta grains. And we have some elements that will precipitate at alpha plate boundaries. And what is important here is that the microstructure after this step will be highly dependent to, for example, the chlorine content. This is two examples with here what we call parallel plates. In fact, here you can see some different colors. It's alpha plates that have the same crystallographic orientations. And in other cases, here you have, I would say, a basket weave microstructure for a high chlorine content. And between this and this, you can have 0.2 ppm of chlorine difference. It's very, very low. We have also other parameters that can change the microstructure, so the heating time. With the coarser beta grains if the heating is long. And depending on the cooling rate, we can have finer microstructure with a fast cooling and also smaller precipitates with a fast cooling. But keep in mind that this type of microstructure can be highly dependent on chlorine content. Then we have the extrusion process. So it's a direct extrusion through a conical die with an extrusion ratio about 10. So it will give us strain of about 2 or 3. And we do this at temperature around 600 degrees. So we are able for sure to model this process. It can give us a lot of data. And in the last years, we included in the finite element model of extrusion one dynamic recrystallization model developed initially by Gourdet-Monteillet and adapted to zirconium by Benoît Godou. So it includes the dynamic recrystallization model during deformation, but also a post-dynamic recrystallization after extrusion. And for this, in fact, we post-process the finite element model results, mainly the temperature, strain, and strain rate during extrusion. And we apply this model in order to predict the recrystallized volume fraction after extrusion and also the grain size. So it's a model based on microstructured fragmentation by subgrains with increasing misorientations up to 15 degrees when we consider it as a new grain boundary and so on. So I think you already know this kind of model, so I will not give details. So coming back to our industrial issue, how we can use this model to improve this microstructure. So this is a very simple example. We saw that at the beginning of extrusion, the flow is not stable, and at the early beginning, the strain is lower. And so we have a lower recrystallization fraction. We can see it both by modeling, it's the lines, and also by experiments, the dots. And it explains us already that if we want to roll this kind of microstructure with some heterogeneities, we will have some cracks. And we know by experience that we have to cut the beginning of the tubes in order to reduce the cracks during cold rolling. And at the end, we can also use this model to modify the extrusion parameters like temperature, extrusion rate, and so on, in order to improve the restructurization rate. I will go faster on this. We have also to improve the surface quality after extrusion. And in fact, this is mainly linked to lubrication process. We know that if we don't have the good lubricant viscosity at the temperature of extrusion, we will have too much or too less lubricants that will give us scratches if we have low lubricant thickness, or faults if we have too much lubricants. And to have the right thickness of lubricant, we need to have the right viscosity depending on the temperature. That's why we need this kind of model in order to calculate the temperature during extrusion of the material. Then we have the cold rolling process. So for tubes, we use what we call the Pilgrim process. Oh, sorry. So during this process, we are both reducing diameter and thickness of the tube by a compressive stress between two rolling with grooved dies, you can see here. And for the tube, there is also a mandrel inside the tube. This is an example just for bars, not for tubes, but you can see already the principle of the process. In fact, after each forward-backward movement of the dies, the tube is turned and moved forward for the next step. I'll put it again. So it means that if you cut a section of the tube from the beginning to the end of the deformation process, it will see the dies around 100 times. So it's step-by-step deformation process. And for this, of course, we try to optimize mainly the design of the dies in order to reduce the damage during the process. I will go faster on this because it's more dedicated on ductile damage mechanics, so it's maybe not the topic here, but we have some models in order to compute the complex mechanical history of the material during the process. We apply on this some ductile damage models. For example, here it's a nice model, but for this we need several tests in order to identify the parameters. And at the end, we are able, for example, for a new die design, to reduce the ductile damage during the cold rolling process. So, as a conclusion, I wanted to show you this slide because I think it's a good summary showing the strong link that we have between the manufacturing processes. So here on this graph, you can see first in blue the chlorine content in an ingot after with solar modeling, and you can see that on the top of the ingot we will have less chlorine because at the end of the melting rate is lower and chlorine have more time to volatilize. And you can see also with, in this case, experimental real ingot, that with a medium chlorine ingot, on the top of the ingot we can have more defects after cold rolling. It's not fully open cracks, but it's just small defects on the surface. And in fact, this shows the influence of chlorine to the final defects on the tube through the microstructure we can have after the quenching process. So on the top of ingots, we have less chlorine, so we have this kind of microstructure that is more difficult to recrystallize, and that can cause, at the end, more cracks during cold rolling. On the bottom of ingot, we have this kind of microstructure, which is easier to recrystallize, and we would like to have this more often, in fact. And in extreme cases, with chlorine content which is lower on all of the ingots, we have many problems. And with a higher chlorine content, we have less defects. But the problem is that we cannot add a lot of chlorine, because at the end we will have other problems like porosities in the material. So you see that we can optimize the recrystallization during hot extrusion. We can also optimize try to optimize the microstructure before, but we need to master, in fact, the whole manufacturing route in order to have the good quality at the end. And this is what I summarized on this slide. To avoid this kind of defect, we can use cold pickering, finite element analysis coupled with ductile damage models in order to reduce the damaging during rolling. We can use hot extrusion finite element model with recrystallization model in order to improve this. We use also modeling of extrusion in order to improve the lubrication efficiency during the extrusion process. But we have also to work on the upstream processes, because we know that at the beginning this is very important on the quenched billets, and this is linked to the chlorine volatilization. So we are working also on the melting process modeling and the core process modeling. So what's next? So as I said, we work on the core process and vacuum distillation modeling. It's not an easy task because it's highly multi-physics modeling. We have also a PhD about VR melting, focused on volatilization models in the solar software. We try also to have a better characterization of quenched microstructure, because in fact it's always difficult to give a classification of this, a number. This is extreme examples, but when we are between the two, depending on the person you're asking, is these parallel plates, basket weave, it's not so clear. So for this kind of characterization, we want to use artificial intelligence algorithms for image analysis. We are working also on the recrystallization models by full field models, so it's the PhD of Victor Grand. And the goal here is to understand why this is more difficult to recrystallize this compared to this, and how we can handle with this. In parallel, we are working also with mean field models within Forge software. So one outcome of this PhD could be new mean field models able to take into account the differences in quenched microstructures. And we have also other alloys, because examples were about zircaloy 4, which is a quite simple alloy. But we have other alloys where, in fact, after hot extrusion, we have remaining unstable second phase, beta phase, that will transform later on in